Hi everybody, welcome to the power generation session. We have two papers, presentations to go through today. So first we have applying design of experiments method for verification of a hydropower system. It's going to be presented by Dr. Marcel.
Thank you. So this paper was originally developed by Lee Pham and Dietmar Winkler, and they were unable to attend. Let me just check here. Okay, yeah, people are here. And the title is Applying Design of Experiments Method for the Verification of Hydropower Systems. This presentation is divided into 6 parts. Okay, we're gonna go a little bit into the background, the design of experiment itself, the modeling of a power plant that we're gonna use as a study case of study. And then we're gonna apply the design of experiment. Here we're gonna present just one of the examples, but we're gonna show the results and we're gonna draw some conclusions about it. Okay, so the first thing that we need to understand is that, well, renewable energy is playing a major role right now in the energy systems. We have been experiencing a big transition in terms of the energy matrix. And what is important here is that, for example, in 2019, wind and hydropower actually made up for 70% of total renewable energy generation. So this is like a big thing. They combined. In this case, hydropower was 35%. And because hydropower actually plays an important role into this renewable energy generation that we are seeing nowadays, it is important to assess it and to study it appropriately. And because also hydropower was already something that we developed since the 1900s, we actually have a bunch of them, and we actually have a bunch of data to use. So we need to actually use that data to appropriately tune our models and to verify if our models actually correspond to reality. So one of the things that we're gonna see here is that even though hydropower has been there for like many years right now, it still has a lot of we still face a lot of difficulties in terms of tuning the models or creating appropriate models, especially for the fluid dynamic part, or like in this case here, we can show the simple simulation model of a hydro plant in your right figure. Oh, sorry, in your left figure. And even like this simple model, like it's hard to actually match the data to your model response, right? And how we're gonna actually try to do that, how we're gonna actually be able to verify the model is by using the design of experiment method. And the design of experiment method actually has 3 main basic principles, let's say, which is the randomization, the replication of it, and the blocking. I'm gonna go over these concepts while I present one of the examples. So the key steps of the design of experiment is actually to recognize the objective and then to select the response that we want to do the design of experiment. We select the process of variables that we want to vary. We perform the experiment and then we interpret the experiment results, right? So as an illustration of that, we're gonna model we're gonna try to pronounce it, Grunnȧi. I think this is close enough. This is a power plant located in Norway, in the municipality of Seljord in Telemark, Norway. And the hydro plant parameters can actually be seen here. The main idea here is that on your left, you're going to see the design, the overview of the structure of the plant. So you're going to see that the reservoir stands at 387, if I'm not mistaken, meters above the turbines 1 and 2. So this is a 2-turbine power plant, hydropower power plant. The discharge is actually 7.5 cubic meters per second. And here we're going to see that the inlet is actually divided into two tubes, 1 and 2. And then after tube 3, they actually get divided into two flows, two streams, one that goes to turbine 1 and the other one that goes to turbine 2. And then they, after running through the turbines, they actually are connected again using this steel pipe, as you can see in number 10 here, if I'm not mistaken. And this conduit actually composes the outlet together with pipes 10 and 11. Okay. So the two turbines are actually Pelton turbines. They are pretty similar in terms of nozzles, but they are different in other parameters. For example, efficiency, nominal power, but they are like close in terms of rating. Okay. And here we're gonna use two sets of data. Okay. And also it's important to say that to validate, we are going to use those set of data to validate the simulation models. And these two data sets, they are coming from basically they are recorded at different times, okay, different points in times and in different operation conditions. So we actually have no cross correlation, no cross relation between them. So it makes our validation better in terms of correlation. The first data set, as you can see in your left, has the water pressure and the flow rate, while the second one has basically the generated power and various input nozzles in the opening valves, both for turbine 1. While the data set 1 is from turbine 2. Okay, so the modeling of the power plant is developed using the OpenHPL, which is an open source hydropower library, which consists of hydropower units that are modeled using Modelica. So simulation as it is, that diagram that we saw before in red is now closed here using Modelica components. And the three basic components of the design of an experiment are applied in this model here, in this model verification procedure. So the first part is the blocking. So in the blocking, we actually divide the hydro plant in three different parts. So we can actually, at different experiments, we can actually validate them separately. Okay. So the first part, the first block is the inlet subsystem or inlet system. Then we have the turbines, and then we have the outlet system. Okay. And we're going to use those two data sets to plug in here and to be able to validate different parts of the system. Okay. So the principles of the repetition part and the randomization part, they're going to be applied to these blocked parts, so to these division parts, those divided parts, and so we can actually be able to gain some estimation in the experimental error. Okay, and here we can show just one of the experiments that are presented in the paper. And the idea here is to develop the mathematical model which relates the generated power to the input signal in the turbines. And this input signal here is the main opening value of the turbines, while the output is just the generated power of the turbines. So the mathematical models of the two turbines that are obtained through the procedure are shown here as the T1 and T2. As expected, they are similar, but they are different due to the different parameters that we saw before, the ratings and also the efficiency and all the different parameters that we summarized. But here we can actually see that the experiment and the measurement have a very good accuracy, meaning that the DOE was actually well executed. And These equations, of course, will be used in further research in controlling and predicting the generated power of the turbines. So, just as a conclusion here, so DOE was a distinct method to simplify the solution for the simulation model. And of course, there's a bunch of difficulties inside of the simulation, but here we presented just one of the examples that are shown in the paper. Well, it can be done under the available measurements as a prerequisite, right? And each portion of the model, since we use the blocking part, can be tested internally to verify and to optimize the design of the entire hydro plant, considering the different blocks. Of course, we saw that the simulation could be used to validate the data that was presented. And this paper also contributed as a simple solution to verify and optimize these terms of these various types of simulation models in the complex systems, which are hydropower plants, which are also multi-domain models. So they actually have multiple different parts, different blocks, and different procedures composing the hydropower generation. So it's actually a very nice, a very interesting first step towards this kind of application of design of experiment to validate complex systems. So thank you for your attention. I believe Dietmar is actually online here to answer any questions that you might have. Yeah, so if you guys have any questions, you can also exactly, you can always contact him via email. Okay, thank you.
Okay, so I am presenting this paper on behalf of Iker Landa del Barrio. And this work was carried out at Vicomtech, which is located in Donostia in the Basque Country of Spain. And the work is together with his advisors from Vimotech and Nayaria Aguinaco, who is from UPV/EHU, which is the public university of the Basque Country. So I didn't participate in this work, but I'm helping Iker, who is right here on my ear in case I need some help. All right, so the overview of the presentation is to give you a little bit of the scenario and the solution that they implemented and just discuss briefly some results. So let me show you what they are trying to do here. So here you have a picture of the campus of a university in the southwest of France. This is in Bidart, which is very close to the Basque Country. And highlighted in yellow is the campus that they're that is going to be subject to the study here. So the idea is to develop a simulator which helps to generate synthetic data that is realistic for two things: loads that have no monitoring and PV generation, for which there is very limited monitoring. So that's basically the idea, to have a model that has the some representation of the power consumed, electrical power consumed, and the power demand. Now, the interesting thing is that the power demand is mostly heating. So it's temperature dependent. And the idea of this simulator is to serve, or the whole solution that they develop is to test and design demand response strategies by changing set points on the electrical loads, and then try to test them in the real system, in the real campus facility. Okay, so let me show you the next slide. So here in blue and in red, you have two sets of data. One is for the winter and one is for the summer. So in the blue one, you can see the demand, the power being consumed. And you can see in the winter is quite larger than in the summer. And that's because the majority of the consumption there is for heating. So the HVAC system, basically. Now the campus has its own photovoltaic production. And what they want to do is to be able to mostly operate the building, in this case, completely as much as possible out of the PV production. One thing that they have found is that selling the electricity and then buying the electricity selling the electricity when they have production to the network and then buying it back is really not economical. So the idea is that, okay, let's just buy the least amount of electricity as possible and be as self-sufficient as we can. So that's kind of the basic premise for the strategy. Now, the demand response program that they're setting up cannot really be applied because they don't have monitoring for all of the loads. And then you don't know really how to apply the set point changes that you need to do. So the available information that they have is 1 year of the demand, which is displayed there. And the other information is 2 months of PV production. Now, that's what's available if you wanted to make some decisions, but that's insufficient. Now, the good news is that they do have access to the weather data directly because it's in France. And in France, there is a public agency called Meteo that gives you all of the weather data. I mean, you have to probably you have to get a subscription for this kind of application, but publicly, that's what they use everywhere in France. And they have the physical information of the equipment. So naturally, to be able to estimate things that are not monitored, you could use a model to achieve that. And that's the basic premise. Now, in the scenario here, the idea they have is they will select specific loads to apply the demand response. The HVAC, which is basically mostly air heating, it's about 15 kilowatts, and the time of use is variable because it's naturally weather dependent. They also have a water heating system for sanitary purposes, which is also weather dependent because you got to heat it up when it's cold. And then the electric car battery charger has been assumed to be a total time of use of 3 hours and is 11 kilowatts. And that's basically because of lack of information on how the whole battery charger characteristics are functioning and no monitoring. So now, because there is neither monitoring for any of these things, just an aggregate demand for the whole building, that's the only monitoring available. The idea is that, okay, if you model the HVAC, the water system, and the electric car battery charger, you could try to estimate what their individual consumptions are, okay? And the same thing for the PV. Okay, so the solution then is to try to build some models of the different parts of the energy sources and the loads, and estimating the energy needs for those, or the demands for those that are not modeled, and use this later for demand response. That part is not covered in this presentation. Okay, so what they have done is to develop a model of the photovoltaic production that includes the weather data, basically radiance that they are getting through Meteo, the meteorological data. They're using, including DC to DC converter, which is a little bit strange, but the idea here is to calculate the total kilowatt power production. So you can model this as a DC equivalent and calculate from that the total demand. So you don't care of what the kilovolt amperes are, only the kilowatts. Okay. So the DC to DC converter that you see in the screen, that basically is an average model because they really are not that interested on any of the other characteristics like the voltage or for example. Okay, so the estimator that they have, so the estimation part here is to use the maximum generation capacity using the weather conditions from Meteo, but they will neglect losses due to orientation, shade, conversion, and conduction, which will at the end be reflected on the estimation that we have that is a little bit larger than what is measured. The PV cell surface temperature is calculated with this equation that you have at the bottom. That is a model presented by Duffy and Beckman in 2013, and it allows you to calculate the input to the PV cell as a function of the irradiance, external temperature, wind speed, and allows you to calculate the surface temperature dynamically. The other parameters used from manufacturers, irradiance at nominal conditions, the cell, the ambient temperature at nominal conditions, the efficiency of the modules, and the product of transmissions and absorbance. The model actually is nice because it was built on top of two different Modelica libraries that are open source. One of them is PV systems and the other one is photovoltaics. So for example, the PV panel and the MSL. The PV panel is from PV systems and the power convection block and the maximum power point tracking algorithm is from the photovoltaics library, and the rest is from the MSL. Okay, so that's about it. So that one model for the source, then you simulate the PV source, and then you inject the result here as an input into the electrical model. So this model is simplified on the left-hand side. You can see here, right there. That's the input of the PV produced. Here there is a source to model the connection to the grid. So if there's any changes on the loads, it will be basically reflected on how much power needs to be delivered by the connection to the grid. You have here the battery charger all the way on the right. And yeah, I think, okay, yes. And then you have the HVAC consumption, and the boiler consumption is in the next slide. So here you have the two real inputs that you have here is to drive the HVAC consumption, which is just hot air, and in two different rooms. Okay. Now the next one. Okay, so the next one is to simulate the hot water tank. So basically, you have to heat up the water. To heat up the water, you have the model that they have is that it will be the consumption will be triggered by this pulse block for 15 seconds every 20 minutes. And it has a hysteresis controller on the right-hand side for the refilling. The resistance will heat the water and keep it around 60 degrees, which is the typical for hot water accumulators. And then the power demand estimated is the power to heat. Now the pump is so small compared to the power used to heat the water that it can be neglected in this case. So that's what they have done. All right, so now here you have a simple model that aims to emulate the thermal demands, thermal loads of the system. So The idea here is to calculate the losses of the exterior as well as the thermal, consider the thermal inertia and the envelope of the building because you have a heat due to irradiation from the sun. So you will have a change. So both the heat sources are included are the HVAC and irradiation, and they contribute in parallel to heat the objecting rooms, and the rooms are modeled here with the with a volume. Now the heat losses with the exterior are calculated dependent on the external temperature and the built-in envelope thermal resistance or admittance. And this resistance has been calculated according to the French regulations for thermal insulation. The thermal contribution of the HVAC system is also calculated dynamically using some commercially available model, which provides data for the COP. And that allows you to take into account also the thermal contribution into the system. This data is interpolated with some tables and allows you to estimate electrical demand. The COP is basically the coefficient of performance, and this is a measure used for HVAC systems that relates the heating power and the electrical demand of the system. And this is typically dependent on the temperature outside and inside. All right, so all of these little models that you saw, they are separated and they're integrated into a solution. In order to automate this process, there is two main parts to take into account. All the automation has been done through Python. The simulation portion is by calling Open Modelica via Python, and this is integrated into an environment programming interface. Now, there's two pieces to the execution. One is the right here on the right. I don't remember what it says. Weather data downloader, it says. That's basically to establish the communication with the French agency Meteo to get all the weather-related information. And the simulation manager is basically going to link the data from the weather and help automate how to run each of these models in a sequence. So instead of making a single model, these models are done separately, and the reason that I was explaining is a problem of simulation efficiency that they have. So it's easier to simulate three separate things than one big one on its own. Basically, it's very logical. Yeah, I believe that's the gist of it. The last thing that you see here at the bottom is interface with the EMS. That's basically right now will allow them to emulate actions that could be applied due to a demand response program, but that's not done in this paper. They are working on that, from what I understand. Ike will correct me. All right, so here are some results that they obtained. The PV generation, as I mentioned at the beginning, they only have 2 months of data. So what they are doing is that they're going to check if whatever they're getting from the models makes any physical sense by using the available PV data and the weather data from Meteo. So you get here in the black is the simulation result, and in the yellow at the top, that is the measured data. Of course, you know, the measured data is an average over time, so you only get a few points, whereas the simulation covers a broader range. So this fast shifting that you see is really due to the changes in the weather data, okay, which are not really captured by an average measurement on a PV panel. You're just seeing an average value there. So to check if things make sense, they basically did some filtering of the power profiles, and what they found is that basically the difference between the actual measurements on average and the simulation is due to the parts that they neglected related to losses on the PV part. Okay, so this basically can allow them to more or less tune and make some predictions on the available PV power of their system. Now, this is quite interesting. This is the estimation of the thermal load in terms of electrical demand. So as you might recall, there's no measurements for that, but there is a measurement of the aggregate electrical power consumed. So in the green line, you have the aggregated consumed power, and in the yellow line is the value that you get from the model. So in order to check this, you can see clearly that when the electrical demand increases, it's largely driven by the heating demand in the buildings. And it's quite interesting that you can even catch quite a bit of peaks at the top. Now, right here at the middle, you see that that's a day that didn't require a lot of heating. So basically, the model says that there's no heating consumption, versus on the 2 other days where the demand of the heating goes up, and you can clearly see that it's increasing the total demand in the building. Yeah, I think I covered everything. I might have missed something. Okay, so that gives you an overview of the work. And do you have any questions? Yes, I have finished. You were trying to. So I got Iker here on the phone in case there's any question I cannot answer. And he can tell me if I did okay. Did I do okay, Iker? He says I did okay. You can't hear him, so I can tell you whatever I want. He's laughing. So Iker, they are asking me if you're going to make the model available or not. So he's saying that he has to ask his managers. But you can get in touch with him. He's a very friendly guy. Maybe he will invite you to San Sebastian too. That's one of the best places in Spain. So yes, go ahead.
You mentioned that
Well, yeah. So I can answer from my own point of view. Irradiance is what matters the most, but the problem is that the performance of the cell you have all these cells and then you have arrays. It will vary completely if you get shadows. If the temperature changes, you get different performance for them, and also there is aging effects. So if you want to get a very good estimate of how much you're going to get from a PV panel, you really need to consider even the angle of inclination that you have and all of these factors. So the hotter it is, the less performance you get out of the PV panel. The colder is actually better, a grosso modo. No, for that you need other models. But I guess if you have real measurements, you could. But they don't have any. They only have 2 months of measurements that was used for the validation, and now they want to use those models for decision making, right? So that's the idea. Yeah. Yeah. So Iker is telling me that for his case, what's most important is to try to figure out what is the maximum production. So any things that you don't get from the panel, right? Not the inverter. The inverter you have to hang wait because there's so many losses there, and then it will take forever to run these things for the switchings. Okay. Right. Next one. Okay, Iker, ojalá que no me
Well, hi everyone again. This work was actually done together with Giuseppe Laera, Fernando, Sergio Dorado, Luigi, Shihab, Chetan, Kevin Jones, and Matthew Gardner. And this presentation will actually be split into 6 sections. So we're gonna talk a little bit about the background of using real-time simulation in power systems and what is the bottleneck that we want to address here. We want to talk a little bit about the model configuration and the framework that we propose. We're going to use and describe some test cases. We're going to present the simulation results and also the simulation setup. And we're going to draw some conclusions and future work. But the main idea here is that, well, power system simulation also, like always, relied on accurate model and simulation techniques. And this is from since the very beginning. So several strategies have already been developed for that. And we are talking here about hand calculations to small miniature models to then the analog computers after the development of the analog integrators. Later on, around the 50s, we actually have the digital revolution. So we ended up having the development of digital computers, and this accelerated the usage of modeling simulations, especially in power systems, in terms of very efficient algorithms and very efficient procedures. And a specific background on real-time digital simulation is that around the 90s or 80s, they started trying to develop efficient algorithms, efficient solution algorithms to be implemented in digital signal processors. And this is where actually the real-time digital simulation was born. And this is very important for power systems because real-time digital simulation is actually one of the last steps that you do before actually implementing a solution in real life. So you test it in real-time simulation to see if it's actually compatible with real-time compliance. And nowadays, for real-time simulation, we usually implement fixed step solvers, and this is basically for some time requirement. It's easier to implement and to be able to ensure compliance with the real time in terms of, well, you need to actually put the inputs into your model, execute all the calculations, and then retrieve the outputs, and you still be able to do that within the time step. And when you don't do that, you actually have an overrun. It doesn't mean that your simulation is invalid. It doesn't mean that your simulation is like completely lost. It just means that that time step doesn't comply to real-time simulation or at that particular step. Okay, so what are our motivations here, right? The current approach in the real-time digital simulation is that you actually use a bunch of different softwares that do not communicate with each other. So this actually talks a little bit with Scott's presentation early today, where you actually have to re-implement the model. In this case, it was re-implemented code, but re-implemented model, and across platforms, across softwares. And this is, of course, like a big bottleneck, especially if you're talking about production, especially if you're talking about testing solutions. So you're gonna actually have one software for the offline simulation, for the design, and then another software for control design, and they don't communicate to each other, so they don't actually have, they are not using the same model. They were re-implemented. And then another one for the real-time testing. So it's a clear lack of portability and tractability, and this is what we wanted to test in this work. And what we want to actually try to do here is using Modelica and the FMI, leveraging those standards to be able to do a cross-platform thing. So from offline simulation, and if you do the offline simulation using Modelica, you are actually enable control design to be done also. And then from offline to the real-time digital simulation using FMI standards. Okay, so the framework that we're going to use here is basically divided into 3 steps. So the first step is the Modelica model configuration. So in this case, we are using Daimler here, and we are using the OpenIPSL, Open Instance Power System Library, which is developed by LSET Labs group. And we create the model of a power system here. For those not familiar, this is a phasor representation. So it's an equivalent representation of a power system. And it's perfect for transient stability dynamics, which means that we are thinking about RMS values. So voltage magnitude and voltage angle. We are not looking, for example, in this case, for an EMT simulation in which you're looking to much more detailed operation of devices. We configure the Modelica model, and in this case, the only configuration that we do is just to put for how many seconds we want to simulate it, and if we want to put some outputs. So if you, for example, are doing some hardware in the loop simulation, you need the outputs and inputs, right? So in this case, we just add outputs here, just so we can read using an oscilloscope, for example. Then we go to the step 2, in which we import the FMU that was generated using the Modelica model and Daimola. In this case, it's a co-simulation, okay, 2.0. And the FMU is loaded into a configuration desk, so you don't need to configure anything else. You just need to load it there, and just put the outputs into your I/O board. So if you want to read those, you just link them, right? And then the last step is just to use the build application, the build real-time application from configuration desk to the real-time simulation. In this case, we use DSpace Galaxio, and all is done using the FMU natively. So we don't use any additional toolbox or additional path or anything like that. So the first system that we test here is an SMIB. So it's a single machine infinite bus. So the machine that you see on your left, okay. So you see some vertical bars. Those are buses or nodes in an electrical system. They can represent, for example, a substation. So on your left, you see a more detailed model of a machine. So you have a electromechanical model of a machine with excitation controllers, also some stabilizers. We have one load, a fault, that is applied in bus called fault. And we have another machine on the right side of the system. And here in the listing 1, you see the configuration of the outputs. You see that it's pretty simple. I just put some of the variables of the model to be outputted as real outputs using Modelica. This model, in terms of size, is 369 differential and algebraic equations. It's not that big at all. It's simulated by 20 seconds, and there is a fault applied at 2. And as you can see, some of the outputs we actually had to put, for example, 2 plus something. And this is basically because since we are measuring it using the output board, I/O board from the real-time simulation, so we actually using the oscilloscope, we actually need displacement because the I/O board doesn't comply with negative voltages. So we just shift them up just so we can measure everything without any distortion. And the second system here is the IEEE 9-bus 3-machine system. It's slightly larger than the previous system that I showed you. So it has 476 DAs, 29% larger. And it's also simulated for 20 seconds, and there is also a fault applied at 2 seconds. And the outputs here are implemented as shown in listing 2. Once again, we actually have some displacements just because of the negative issue with the I/O board. And for the real-time simulation setup, here we have actually the host computer. It is connected to the real-time simulator using an Ethernet cable, and then from the I/O boards that you can see, you don't see the pointer, but from the I/O boards here, we can actually connect all the measurement devices. Here in the screen, we are actually showing a digital oscilloscope and a real oscilloscope. Yeah, and also the parameters of the hardware and the simulation is that we are using a 1 millisecond time step, which is okay for electromechanical stability studies in power systems. We set the over and maximum number to be 150. And here we are just using one of the available cores of the real-time simulator. So the first results here are from the SMIB system. As I said before, it's 20 seconds, and as you can see, there is a fault happening. So the top results actually show you the terminal voltage. It's a magnitude voltage, okay? It's in per unit in red. And in blue, you actually see the deviation from nominal frequency that you see on the generator. And as I said before, you actually have a displacement from the real value because of the I/O board issue with a negative value. And in the bottom, you see the generator's electrical power output in red, and in blue, you actually see the rotor angle. Okay, and I believe they're like the power is in per unit, and the rotor is in radian. The rotor angle is in radians. And for the second system, the IEEE 9-bus 3-machine system, here, since we had a STATCOM connected to it, it presented a bit more overruns than the simulation that I showed you before. I'm going to discuss a little bit later. But the top figure displays the reactive power from the STATCOM in red and the one from the generator 1 in blue. And then in the bottom figure, you actually see the deviation from nominal frequency in generator 1 in red and 3 in blue. And as you can see, you see like a much broader pattern, and then you see like kind of the average in the middle. And that's basically like the average and the noisy measurement. And this is what actually is important when you're trying to do, for example, a hardware in the loop simulation to test your controllers and how it's able to reject noise, for example. So another interesting thing here is that we were able to use demo to perform some interesting analysis concerning the overruns that were observed during the simulation. So here, here we can, it actually allows the engineer to understand the selection of the time step for the real-time simulation before actually executing the real-time simulation. So you are actually able to see how many overruns you're gonna encounter if you choose a certain type of time step size. So here you see that the SMIB system, which has 369 DAEs, had approximately 18 overruns total, and an approximate turnaround time. So the turnaround time is the time that you take to read the inputs, do the calculations, and perform the outputs, make them available. So here's 83 microseconds. But if we go to the IEEE 9-bus system, we see that even though it's only 29% larger, it actually had much, like 109 overruns total, and at 268 microseconds to do the test turnaround time, which means that even if you increase just slightly the size of the model, it becomes more and more complex to do the calculations for the real-time compliance. And this is something interesting, and we actually want to take a look at that in future works. But here for the conclusions, what is interesting here is that we presented a framework that allows power system simulation studies to be conducted from offline simulation to real-time simulation with minimal modification and no re-implementation at all. This was done by leveraging the features from Modelica and the FMI standard. So this was really, really interesting. And this adoption of this framework allowed us to increase the portability and tractability of power system modeling. And this is very important in the present context where we actually have a bunch of different softwares and a bunch of different, let's say, stages in the production. And as future steps, as I said, one of the things is that we can divide the system into multiple FMUs, use the multiple cores to actually reduce that the test turnaround time for much complex systems. In this case, we were using a smaller real-time processing unit, so it has potential to be scaled up. And we can also highlight here the possibility of performing control hardware in the loop simulations, in which we can do the offline simulations, optimizations, control design, everything using the Modelica model. And then when we are going to test everything, we do it in real time without any model re-implementation. And even by using this new EFMI, the control part could also be exported directly, so you don't need to actually re-implement every step. So this is actually pretty good in the portability in terms of power systems, which in the present context, we don't have much portability and tractability. So yeah, finally, I would like to thank Dominion Energy, KAUST, and the Department of Energy for supporting this research. And thank you so much for hearing to this presentation. And should you have any questions, please shoot me an email here in this address, or ask me something like here. It has some time. It has some time. Yeah. Yeah. So in the transient, we actually have a much more complex, like it changes the system abruptly. So it's a fault, a three-phase to ground fault. You're changing like the system a lot in not like it's a step modification to your system. So it makes it harder to calculate the solution. No, the equations end up like changing, like the system equations that you're gonna solve are gonna change because the system changed. So three. Yeah.
Another thing is the dynamics actually get all we're doing that gigantic. Well, no, I understand there's a transit, but if it's a fixed step solver, it's explicit, it doesn't care. But you have a transfer structure for a few reasons. So why is it that like periodically, very periodically, like
yeah, this is also something that we wanted to analyze, because here also you see like that sometimes it appears like the overrun appears during the simulation without any particular change, but you see that like basically we see the overruns in the initialization like 6, or I think in this case here 2, but in the other one 6, and then you see it on the disturbance, and then after the disturbance you see them like sometimes, but this is actually something that we want to analyze, like what's happening. We actually are doing some here in this case we actually did an analysis to see what state were actually contributing most of the error. We actually saw that the excitation system states, which are like the faster ones, like the really fast ones, were the ones contributing to the error here. But this is actually something that we are totally like trying to look into why this happens, like in the way it happens.
But I would say that it's not for running that almost have states over. Usually we do related to any of the control. Now everything happens. Some of the cycles cannot do it. So no, but we cannot define the answer with whatever they found. The way to deal with this, I think, is when you get too many on the run, you have to split the model in different cores. But these models are very tiny, so people do it. So maybe the challenge to use scalability and going forward. These are probably examples of these. They are not real world. How big is the real world model? The Icelandic model?
Well, we can use the simplified New York model. It's 64,000 DAs.
We haven't done that in real sense.
No, actually, like during the execution, you actually see how many overruns were observed. From the display software, yes. Yeah. How many overruns? Sorry.
Is acceptable?
Yeah, this was actually like I didn't consider that. Like didn't consider like, oh, this amount of overruns is acceptable for this simulation. But I think you actually can find in literature some at least some benchmark experiments in which they set a number of overruns for your real-time simulation. But in this case, I just set like a maximum, so you could actually run both simulations. So I could actually do the analysis and check if the number here that you see here matches with the number of overruns that you see in the simulator, and they actually match, and you actually can see them.
The overruns are really that matter if the ones are close together.
Mm-hmm.
The closer they are together, the worse, because basically you cannot update the value of the new state or the new output that you want. You have the old one, but you're not able to update it. So if you have anything very close together, that's a problem, because if you're feeding using the hardware inside, hardware doesn't know something has happened, so you cannot update the output. But when you have one in a while, not such a big deal because of the encoder that you have outside as hardware won't notice it. It also depends on the what is it called, the execution time that you have for the embedded system versus what you're running. So if your embedded system is lower, doesn't matter. The overruns happen, the model updated, and your hardware has not been sampled. So it really depends on, it's very application specific.